this section in trigonometry, we want to talk about the sum and difference formula. And what I have here for you is an example of where you might use a sum or difference formula. Notice we're taking the sign of a sum, the sign of pi over 3 plus pi over 6. Now, what I want you to realize, what you cannot do, so this is a big don't do, and I'm going to show you why, is you cannot think about this as the distributive property. This is not equal to the sine of pi over 3 plus the sine of pi over 6. So do not allow yourself to do that. It's just not true. I can show you why if we handle this. We can calculate the sine of pi over 3 plus pi over 6. You know, that's equivalent to saying this is the sine of, and we could add these two fractions together by saying pi over 3 is equivalent to 2 pi over 6 plus pi over 6, which is equivalent to sine of 3 pi over 6, which is equivalent to the sine of pi over 2. And of course, the sine of pi over 2, remember you reflect back on your unit circle, here lives pi over 2. That's this angle right here. The sine of that is the y value right there is 1. So the sine of pi over 3 plus pi over 6 is 1. Now, had we done it this way, you would have the sine of pi over 3, if you remember that, is going to be the square root of 3 over 2, plus the sine of pi over 6 is 1/2, and notice clearly that's not equal to 1. So it's not allowed to distribute a trig function inside. This is not multiplication. This is a function. So in this particular problem, we didn't need a formula to simplify this expression, because when we added pi over 3 plus pi over 6 together, we got a value on the unit circle, sine of pi over 2, and we were able to evaluate that. But what if you added these two together and it wasn't a value on the unit circle, so you would have to use your calculator and you couldn't get an exact answer? Or what if one of these values was a variable and not an exact angle at all? Then you would need a way to simplify this expression. Okay, so what we have here are the sum difference formulas. Notice there are 6 of them. We have 2 for sine, a sum and a difference. We have 2 for cosine, a sum and a difference, and 2 for tangent, a sum and a difference. We don't have formulas for cosecant, secant, and cotangent, because if you needed those values, you could just do the reciprocal of sine for cosecant, the reciprocal of cosine for secant, and the reciprocal of tangent for cotangent. Now, like I said, you do have to memorize these formulas, so you need to come up with a strategy to help you with this. Notice for the sine, notice what they have in common. Sine is of the form sine of A, cosine of B, cosine of A, sine of B, and addition here is also addition here. So notice the trig functions alternate. So if it helps to memorize this, remember for sine, the trig functions alternate. The angles stay in the same order. Notice it's alpha plus beta, then you have alpha, beta, and again, addition is still addition here. So notice for sine of alpha minus beta, it's sine of alpha cosine of beta. Again, the angles stay in the same order, the trig functions alternate, and the operation matches. Okay, so for sine, again, the trig functions alternate, and the operation matches. For cosine, it's the opposite. Okay, so notice for cosine, whatever operation you're doing is the opposite, and the trig functions don't alternate. It's cosine, cosine, sine, sine. So notice you look, if you have cosine of alpha plus beta, it's cosine of alpha, cosine of beta. Change the operation, sine of alpha, sine of beta. Okay, again for cosine, it's cosine of alpha minus beta is cosine of alpha cosine of beta. Again, if it's minus, you change it to plus, sine of alpha sine of beta. Okay, and then for tangent, notice that first of all it's a fraction. whatever operation you have here is the same operation you have in your formula in the numerator, okay? And in the denominator, it's the opposite, okay? So if it's a plus, you have a plus in the numerator and a minus in the denominator. Tangent for minus, you have a minus in the numerator and a plus in the denominator. Other things you have to remember is the format. So notice tangent, it's almost like a distributive property up here. You see what I mean? Tangent of alpha plus tangent of beta. It's almost like you multiplied that inside, which we know is not allowed, but it might help you memorize the formula. And then in the denominator, you have 1 and then the opposite sign of tangent of alpha, tangent of beta. Okay? Again, notice for this one, for the minus, you have tangent of alpha minus tangent of beta. Again, almost like you use some sort of weird distributive property. And then the denominator, 1, you change the sign, and then those same two trig functions multiplied together, tangent of alpha, tangent of beta. Okay? But now, I'm giving you these and just asking you just to memorize them, but I would like to show you at least where one of them, maybe two of them, come from proof-wise. Okay, so that's what we're going to do next. All right, so what I have drawn for you here is a unit circle with several angles marked off. So if this is a unit circle, you know the radius is equal to 1. We'll use that to label a point in just a minute. But let's talk about what angles we have here. Now when you look at what we're trying to do is we're trying to prove that the cosine of alpha plus beta is cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. Okay, so maybe on our unit circle we need an angle for alpha and an angle for beta. And I called alpha my smaller angle, so I'm going to say this angle right here, there's alpha, okay? And I called beta my bigger angle, so this angle right here, okay, is beta. Now, it may not be exact because I didn't measure this out, but what I wanted this to be, this angle down here, the green one, is this same angle value of beta, but since it's going this direction, that's going to be negative beta. Okay? Now let's use this to label the points on our circle. Now I know you know any point on a circle is an x value, y value. Okay, so this point right here, okay, is going to be the point 1, 0. Now remember why it's 1, 0, right? Because this is a unit circle. This is a regular xy axis. The radius of this circle is 1. That's why the x value is 1. And then, of course, you're on the x-axis. That's why the y value is 0. Okay? Now, let's label this point where the terminal side of alpha is. Now, again, it's an xy value. But since we know this is the angle alpha, remember that the cosine of alpha is your x value. Remember, on the unit circle, cosine is your x value, sine is your y value. So this would be labeled cosine of alpha, sine of alpha. Okay? Now let's label this point right here, and I think I'm going to label this guy in red. All right? So now, this is the terminal side, not of beta, right? This is the terminal side of this entire angle because you have to start your angle in standard position. So if I go from here all the way to there, that x value is going to be the cosine of alpha plus beta, and the y value is going to be the sine of alpha plus beta. Okay? Now finally, let's label this point down here. All right? So this value down here, this angle is negative beta from standard position. Okay, so the x value is the cosine of negative beta, and the y value is the sine of negative beta. Okay, now why in the world would I do all of this? All right, well, here's what we're going to do. I'm going to draw a line for you, and then you tell me, you think about this and see if this makes sense to you. So I'm going to connect, and it's called a secant line where you connect 2 points on a circle. So I'm going to connect, and let's do this in a different color, this point to this point, okay? And assume that's a straight line. And then I'm going to connect this point to this point. Now the argument is these two straight lines that look real squiggly, I know, again, this is a slippery screen I'm writing on, but these are the same length. Now, I can't argue they're the same length because they visually look the same length. As a matter of fact, to me, they don't even visually look the same length but that's because I don't have this angle beta drawn exactly to this angle beta. It's just an assumption. It's just a quick sketch. But now the argument is they have to be the same length because this angle that we're connecting right here is alpha plus beta. So then the line across there has to be the same distance. This angle is also alpha plus beta. I know this is a negative beta because it's going backwards, but the full angle, the full positive angle is still alpha plus beta. So my black line here must be equal to my gray line here. Now, here's where the fun part starts. So I could call this black line D1, and my gray line, I could call it D2. Now what's important here is D1 must equal D2. And again, from geometry, that makes sense, right? Lines across from the same angle have to be the same length. So let's use the distance formula to find the length of D1. Let's use the distance formula to find the length of D2, and then we will set these two distances equal to each other, and believe it or not, it's going to prove this theorem for us. Okay, so the distance formula, you do remember that, right? So I'm going to sneak it in over here. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, all underneath the square root. So, of course, my x's and y's are labeled here for me. So D1, I'm going to say, is the square root of x2, which is cosine of alpha plus beta, minus x1, which is 1, and this is all squared, okay, plus y2, okay, so that's sine of alpha plus beta, minus y1, which is 0, squared. That's all underneath the square root. Okay. Now we could go ahead and simplify that. Notice I haven't found D2 yet. Okay. I'm just going to simplify this expression the best I can. Now that's going to require some work. We need to FOIL this out. This is going to be cosine of alpha plus beta minus 1 times cosine of alpha plus beta minus 1 plus, now this is minus 0, so that's going to be sine squared of alpha plus beta. Okay, so you see what I did? All I've done so far is write this out twice, and then I subtracted minus 0, which just gives me the sine of alpha plus beta, and then I squared it, and the way to write that is sine squared of alpha plus beta. Now I'm going to use the distributive property to do all this fun activity. Okay, so that gives me cosine of alpha plus beta times the cosine of alpha plus beta is the cosine squared of alpha plus beta. Then cosine of alpha plus beta times negative 1 will be minus cosine of alpha plus beta, and then minus 1 times the cosine of alpha plus beta will be minus the cosine of alpha plus beta, and then finally minus 1 times minus 1 is plus 1, and then don't forget over here the one we've already simplified, sine squared plus, left all the plus, sine squared of alpha plus beta. That's all underneath the square root, and that is only the length of our black line, right? Now, watch this. This is where it gets fun, okay? Look, I've got cosine squared of alpha plus beta, and I've got sine squared of alpha plus beta. Now, what does that equal to? And now you know what that is. That's 1, right? Due to the Pythagorean theorem, okay? So that gives me, when I simplify this, the square root of 1. Now, these guys are like terms, so minus 2 cosine of alpha plus beta plus 1, which simplifies to the square root of 1 plus 1 is 2 minus 2 cosine of alpha plus beta. Okay, that is D1. So what I want to do is right above here, my D1, I want to write what this is because I need to erase my board and figure out what D2 is. So this is going to give me D1 is the square root of 2 minus 2 cosine of alpha plus beta. And we're going to wipe out this screen and then we're going to calculate D2. Alright, so now it's time to find D2. Let's see if we can set this up again. Over here on the left, I'm using my distance formula. So I have D2 equals, so we're supposed to subtract our x values. So my x value here is cosine of alpha. My x value here is cosine of negative beta. Okay, so I have the square root of cosine of alpha minus cosine of negative beta, and then all of that is squared, plus now I'm subtracting my y values. So my y value at this point is sine of alpha minus sine of negative beta, and that is all squared, and this is all underneath one big square root. So again, we're doing D2 right now. Okay, now I want to simplify this as much as possible. The first thing I need to recognize here is I have to do something with these negatives inside my trig function. This is where we use our even-odd properties. Remember, cosine is even, which simply means the negative disappears. Cosine of negative beta is exactly the same thing as cosine of positive beta. So that's going to be my next line, is to get rid of this negative. So I've got cosine of alpha minus cosine of positive beta, all squared, plus, now over here I've got sine of alpha. Now if you'll recall, sine is an odd function, so what that means is the negative needs to come out front, because sine of negative beta is equivalent to negative sine of beta, and that's going to make that negative a positive. And that's still squared. Now I'm going to do lots of simplifying. I'm going to multiply cosine of alpha minus cosine of beta times cosine of alpha minus cosine of beta, and sine of alpha plus sine of beta times sine of alpha plus sine of beta. So it's about to get big. Alright, so the square root of cosine of alpha minus cosine of beta times cosine of alpha. That doesn't look a thing like an alpha. Let me try that again. I apologize. Okay, so here we go. Cosine of alpha minus cosine of beta plus sine of alpha plus sine of beta times sine of alpha plus sine of beta. I know many of you could probably just multiply that out in your head without writing all this down, but I want to make sure you're clear on every single step here. So now we've got the square root of, now cosine of alpha times cosine of alpha, these two guys, is going to be cosine squared of alpha. Cosine of alpha times cosine of beta, negative, is going to be cosine of alpha, cosine of beta. Okay, it's not like we can multiply those two together other than just writing it out. Now I'm going to multiply, so we've done those two. Now I'm going to do negative cosine of beta times cosine of alpha, but I'm going to write it in the order I just wrote this in, so you can see the like terms. And then finally, cosine of beta times cosine of beta, both negatives, is going to give me a positive cosine squared of beta. Now I'm running out of room, so I'm going to start trying to write smaller. Sine of alpha times sine of alpha is plus sine squared of alpha. Sine of alpha times sine of beta is going to be plus sine of alpha, sine of beta. Sine of beta times sine of alpha is another one of those identical terms. And then finally, sine of beta times sine of beta would be plus sine squared of beta. Way to fit it on the screen. Here we go. Now we're going to simplify a lot. Check this out. I got a cosine squared of alpha, and surely I have a sine squared of alpha somewhere. Right there. Look, cosine squared of alpha plus sine squared of alpha. Y'all know what that is. That's 1. Okay, so I have the square root of 1. Now, what else do we have? I have a cosine square root of beta, and I have a sine square root of beta. What is that? Pythagorean identity, you say? Yep. Plus another 1. Okay. Now I have some like terms going over here. There's 2 of those guys, so that's going to be minus 2 cosine of alpha, cosine of beta. Okay. Plus, those are also like terms, 2 sine of alpha, sine of beta. Okay. One more thing I can do, right? I can add these 2 values together to get 2. So this is the square root of 2 minus 2 cosine of alpha, cosine of beta, plus 2 sine of alpha, sine of beta. So some fancy work with making substitutions with the Pythagorean theorem. Okay, we're not done, right? This is just D2. So I want to write it up here. So that's equal to 2 minus 2 cosine of alpha, cosine of beta, plus 2 sine of alpha, sine of beta. All right? Okay, so remember the entire basis of this proof is based on the fact that line D1 is equal to line D2. Okay, so we spent a long time calculating D1. We spent a long time calculating D2. Let's write down what we have. Now, right up here, I've already got it written equals, and now you can see that clearly. If I have a square root on both sides, that's equivalent to saying these are the same thing without the square root. So really what I have here is 2 minus 2 cosine of alpha plus beta is equal to 2 minus 2 cosine of alpha, cosine of beta, plus 2 sine of alpha, sine of beta, right? Now, these are equivalent. I'm trying to just simplify it. What I'm actually trying to do is get cosine of alpha plus beta on one side and then all this stuff on the other side. Now, if you'll notice, these 2's can just simply subtract out, okay? Those guys are now gone, okay? Let's rewrite what we have. So now I have negative 2 cosine of alpha plus beta is equal to negative 2 cosine of alpha, cosine of beta, plus 2 sine of alpha, sine of beta. Now notice we're almost there. This line on the left almost matches this line here on the left, except we got a negative 2 in there. What do you want to do about that? Well, how about we factor in negative 2 out of the right-hand side, then we could divide both sides by negative 2, and maybe this is exactly what we need. So the left side, I'm leaving alone. Negative 2 cosine of alpha plus beta. Now on the right side, I'm going to factor this common 2 out, but I'm going to pull out a negative 2. And that's going to give me cosine of alpha, cosine of beta, minus, because we're factoring out a negative, it's going to make that minus sine of alpha, sine of beta. Okay. Now, we divide both sides of our equation by negative 2. Those cancel each other out. So I have the last line that reads cosine of alpha plus beta is equal to cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. And there is one of the cosine sum difference formulas. Now, we could do all 4 of our sine and cosine sum difference formulas using a very similar argument, but I'm going to trust the fact that you trust me that it's a very similar logical argument using geometry to get that. So we're just going to assume the other 3 are true. Now I need you to memorize them. Okay?